Hold up your hand for a moment. Right now, without the faintest sign you could feel, tiny particles are passing straight through it, through your skin, your bones, the floor, and into the ground below. They are called muons, heavier cousins of the electron, born miles overhead where cosmic rays strike the top of the air, and most of them live less than a millionth of a second. For more than 20 years, a patient army of physicists has chased one strange fact about them. The way a muon wobbles inside a magnetic field is, by a whisper, not quite what our best rulebook of physics predicts. That whisper might be nothing at all. Or it might be the first trace of a force nature has kept hidden. That is the idea we will build toward here, slowly, one plain step at a time. If you like this kind of unhurried walk through real physics, take a second to subscribe and stay with me. Our question is simple. What is a muon telling us when it refuses to behave? Picture the electron for a moment. It is the small, familiar particle that carries electric charge through every wire in your home, the lightest speck of matter that still counts as matter. Now imagine you found another particle exactly like it in every way that seems to matter. Same negative charge, same spin, same indifference to the strong force that binds atomic nuclei. The only difference is weight. This new particle is heavier than the electron by a factor of about 207, as if someone had taken the electron and quietly poured in far more mass while changing nothing else. That heavier twin is the muon, and when it first turned up, nobody had asked for it, and nobody knew what it was for. The physicist Isidor Isaac Rabi is said to have summed up the feeling with 4 words when he heard the muon was real. Who ordered that? It is a joke, but it carries something true. The electron had a clear job. It sat in atoms, it carried current, it explained chemistry. The muon did none of that. It appeared, lived for the briefest flicker of time, and vanished into lighter particles. It seemed like a spare part with no machine to fit, and yet this spare part has become one of the most useful tools physics has ever held. The reason is subtle, and we will build up to it carefully, but here is the seed of it. Because the muon is so much heavier than the electron, it feels the deep structure of the universe more strongly. It is more sensitive to faint hidden effects, the way a heavier tuning fork will pick up a low note that a light one misses. A muon is, in a quiet way, a better listening device than an electron. The listening happens through magnetism. A muon spins, and a spinning bit of charge behaves like a tiny magnet. Put that little magnet in a strong magnetic field, and it wobbles, the way a spinning top leans and circles when you set it on a table. The rate of that wobble can be predicted, with breathtaking care, by our best theory of how particles and forces work. It can also be measured, with equal care, in a real machine. For most of a century, the prediction and the measurement have been locked in a slow race to see who is more precise, and to see whether they agree. For a long stretch of recent years they did not quite agree. The muon wobbled a hair faster than the rulebook said it should. The gap was tiny, far smaller than a single part in a million, but it was stubborn and it would not go away. A gap like that has only a few possible meanings. Maybe the measurement was flawed, maybe the calculation was flawed, or maybe the muon was feeling the pull of something not written in the rulebook at all, some particle or force that no one has ever directly seen. That last possibility is the reason this story matters. The Standard Model is the name we give to our current list of the basic building blocks of nature and the forces between them. It is fantastically successful, and it is also, we know, incomplete. It says nothing about the dark matter that outweighs ordinary matter across the cosmos. A crack in the muon's wobble might have been the first hairline fracture where something new leaked through. To understand why a single wobbling particle could carry that much weight, we have to go back to the beginning, to a mountaintop in the 1930s, and to two men photographing the sky. The muon did not arrive in a laboratory by invitation. It fell out of the heavens. The muon was not discovered. It was noticed, in tracks left behind by something falling out of the sky. To see how that happened, you have to know what was raining down. The Earth sits in a constant drizzle of particles from space. Protons and atomic nuclei, flung out by exploding stars and other violent events far away, stream through the galaxy and slam into the top of our atmosphere at enormous speed. These incoming particles are called cosmic rays. When one strikes an air molecule high above your head, it shatters into a spray of new particles, which strike more molecules which make more particles. A cascade that showers down through the miles of air until some of it reaches the ground. Right now that shower is passing through you. In the 1930s, physicists studied this rain with a device called a cloud chamber. It is a sealed box full of vapour on the edge of condensing, so cold and still that a charged particle passing through leaves a thin trail of droplets, like the white line a jet leaves across a clear sky. Wrap the chamber in a magnetic field, and the trails curve. A negative particle bends one way, a positive particle the other, and the tightness of the curve tells you something about the particle's mass and speed. A light particle whips into a tight arc. A heavy one barely bends. At the California Institute of Technology, a young physicist named Carl Anderson had already made his name with this method. In 1932, he had spotted a track that curved the wrong way for an electron, and in doing so discovered the positron, the electron's antimatter partner. That work would win him a share of a Nobel Prize while he was still in his early 30s. So when Anderson and his student Seth Neddermeyer carried cloud chambers up to high altitude, hauling them to the top of Pikes Peak in Colorado to catch the cosmic shower before it thinned out, they knew exactly how to read a curving line. What they found did not fit. Among the tracks were particles that curved too gently to be electrons, but too sharply to be protons. Their bending placed them somewhere in the middle, at a mass heavier than the electron, but far lighter than the proton. By 1936 and into the following year, the evidence was solid enough to announce there was a new particle in the cosmic rain with a mass a couple of 100 times the electrons, and it carried the same charge an electron does. They were cautious about what to call it, and for years the naming stayed muddy. In time it settled into muon, from the Greek letter mu. But the caution was wise, because nobody knew what this middleweight particle was, or why nature would bother making it. It was not part of any atom anyone had drawn. It came from the sky, lived for an instant, and broke apart. That last fact turned out to be a gift. Because the muon is unstable, because it decays so quickly, it became a natural clock and a natural messenger. Its short life would later let physicists test the strangest predictions of Einstein's relativity, and its habit of being born already spinning in a known direction would one day let them read its wobble in a magnetic ring. None of that was clear yet. In the late 1930s, the muon was simply a mystery that had fallen from the heavens with no obvious purpose, and there was a deeper confusion waiting. A famous theorist had recently predicted a particle of almost exactly this weight for reasons that had nothing to do with cosmic rays. For a while, everyone assumed the muon was his particle. They were wrong, and untangling that mistake is the next step. Just 1 year before the muon showed up in the cosmic rain, a Japanese physicist had predicted a particle almost exactly its weight. His name was Hideki Yukawa, and his problem was the atomic nucleus. A nucleus is a tight cluster of protons and neutrons. The protons all carry positive charge, and like charges push each other apart. So by the ordinary rules of electricity, the nucleus should fly to pieces. Something stronger has to be holding it together. A force that only acts across the tiny width of the nucleus and then quits. Yukawa proposed that this strong force is carried by a particle passing back and forth between the protons and neutrons, the way two people can stay bound together by tossing a ball between them. From the short reach of the force, he could estimate the ball's weight. It came out to roughly 200 times the mass of the electron. So when Anderson and Neddermeyer reported a cosmic particle of about that mass, the fit seemed obvious. Here was Yukawa's carrier of the strong force, delivered from the sky. Physicists began calling it the mesotron, the middle particle, and for about a decade the identification stuck. The heavy cousin of the electron was assumed to be the glue of the nucleus. There was a way to check. If this particle really carried the strong force, it should feel that force powerfully, fire it into matter, let it come to rest inside a slab of material, and it should dive straight into a nearby nucleus and be swallowed almost instantly. That is what a strong force particle does. It cannot ignore nuclei any more than a magnet can ignore iron. In Rome, in the last years of the Second World War and just after, 3 Italian physicists set out to test exactly this. Their names were Marcello Conversi, Ettore Pancini, and Piccioni. Working with improvised equipment, sometimes moving their apparatus to dodge the dangers of wartime, they let cosmic ray particles slow to a stop in blocks of different materials and watch what happened next. The result, published in 1946, was a quiet shock. When the particles stopped in a light material like carbon, they did not plunge into the nuclei at all. Instead, they lingered, and then decayed on their own, taking a couple of millionths of a second to fall apart. A true strong force particle would never have waited that long. It would have been devoured. The conclusion was unavoidable. Whatever this cosmic particle was, it barely felt the strong force. It could not be Yukawa's glue. The mass had matched by pure coincidence. The knot came undone the very next year. In 1947, a group led by Cecil Powell in Bristol, working with the physicists Giuseppe Occhialini and Sir Lattice, studied cosmic rays using special photographic plates that recorded particle tracks directly in the emulsion. In those plates they found a slightly heavier particle that did dive into nuclei and did feel the strong force. This was Yukawa's real particle, and it earned the name pion. And crucially, they saw that a pion, when it decays, gives birth to the lighter middle-weight particle. The pion was the parent, the muon was the child. So the picture finally sorted itself out. Yukawa's strong force carrier was the pion, and Yukawa would win a Nobel Prize for predicting it. The muon was something else entirely, a particle that fell out of pion decay, and then, having no nucleus to bind and no obvious duty to perform, simply decayed in turn. That left the muon exactly where Rabi's joke had placed it, as the particle nobody ordered. To see why nature would make such a thing, we have to stop asking what the muon does and start asking what family it belongs to. Once physicists accepted that the muon was not a tool of the nucleus, they had to find its place another way. The place turned out to be a family portrait, and the muon sits in the middle of it. Start with the electron again, because everything here is measured against it. The electron belongs to a class of particles called leptons, from a Greek word for light or thin. A lepton is a particle that does not feel the strong force at all. It ignores the glue of the nucleus completely. The electron is the most familiar lepton, light and stable, content to orbit inside atoms forever. The muon, we now know, is also a lepton. It has the same electric charge as the electron, the same amount of spin, and the same deafness to the strong force. In the language of the theory, It is a second copy of the electron, identical in its dealings with electricity and magnetism, and different in only one plain respect. It is heavier. Where the electron has its small fixed mass, the muon carries about 207 times as much, and there is a third copy, found much later, in the 1970s, at the Stanford Linear Accelerator Center, by a team led by Martin Pearl. It is called the tau, and it is heavier still, roughly 17 times the mass of the muon, and about 3,500 times the mass of the electron. The tau is so heavy that it decays almost the instant it forms. 3 leptons then, with the same charge and spin, laid out like 3 siblings of rising weight: the electron, the muon, and the tau. Each of these charged leptons travels with a ghostly partner called a neutrino. A neutrino is a lepton with no electric charge and almost no mass, so faint that trillions pass through your body every second without touching a thing. There is an electron neutrino, a muon neutrino, and a tau neutrino, one for each sibling. When a muon decays, it does not simply turn into an electron. It turns into an electron, plus a muon neutrino, plus an electron antineutrino, the ghostly partners balancing the books as the charged particle changes form. So the leptons come in 3 sets, and physicists call each set a generation. The first generation is the electron and its neutrino, the light and stable pair that makes up the ordinary matter around you. The second generation is the muon and its neutrino. The third is the tau and its neutrino. Each generation repeats the pattern of the one before, only heavier and more fragile. The heavier a charged lepton is, the faster it falls apart. This raises a question that physics still cannot fully answer, and it is worth sitting with rather than rushing past. Why 3? The ordinary world needs only the first generation. Every atom in your body, every star in the sky, is built from electrons and the particles of the first family. The muon and the tau add nothing that ordinary matter requires. They are heavier echoes, born in high-energy collisions, gone in a flash. Nature apparently made 3 copies of a design when one would have furnished the visible universe. We do not know the reason. We only know from careful counting and experiments that there are 3 of these light families and, it seems, no more. The muon then is the middle child of a family whose very existence is a puzzle. That middle position is exactly what makes it precious. It is heavy enough to be sensitive the way the tau is, but it lives long enough to be caught and studied, which the tau does not. The muon is the one heavy lepton you can actually get your hands on. To use it though, you first have to catch it before it disappears. And the muon disappears very, very fast. A muon at rest lives, on average, about 2.2 microseconds. That is 2 millionths of a second, roughly 2,000ths of the blink of an eye. In that flicker, the muon does its one reliable trick. It decays. It vanishes and leaves behind an electron and 2 of those ghostly neutrinos, and the electron flies off carrying most of the leftover energy. 2 microseconds sounds like no time at all, and for most purposes it is not. But it is also, strangely, a long life as unstable particles go. The pion that gives birth to the muon lives less than 100th as long. The tau, the muon's heavier sibling, is gone in a far smaller fraction still. Among the particles that fall apart, the muon is almost leisurely. That relative patience is the first reason it is useful. Here is where the muon delivers one of the cleanest demonstrations in all of physics, and it hides in the cosmic rain we started with. Remember that muons are made high in the atmosphere, when incoming cosmic rays smash into air molecules many miles up. Those muons come screaming downward at very nearly the speed of light. Now do the simple arithmetic. If a muon lives about 2 microseconds, then even moving at light speed it should travel only about 600 meters before it decays. 600 meters. The muons are born 10 or 15 kilometers up. By that reckoning, essentially none of them should ever reach the ground. They should all die in the upper air, far above your head. But they do reach the ground. They pour through you as you read this, in large numbers, far more than the simple calculation allows. For decades, this was a genuine puzzle. And its answer is Einstein's special relativity, shown plainly in falling particles rather than in equations on a page. Relativity says that time does not tick at the same rate for everything. For an object moving very fast relative to you, its internal clock runs slow, seen from your point of view. The muon is moving at more than 99% of the speed of light, and at that pace its clock crawls compared to yours. From the ground, watching the muon race down, its 2 microsecond lifespan stretches out several times over, long enough for it to cross the miles of atmosphere and arrive at the surface. From the muon's own point of view, the story is different but consistent. In its frame, its life really is only 2 microseconds, but the atmosphere ahead is squeezed thin by its speed, so the trip is short enough to survive. Either way you tell it, the muon reaches the ground, and it does so because of relativity. This was checked directly. In 1941, the physicists Bruno Rossi and David Hall measured how many muons survived at the top of a mountain and how many made it to a lower altitude. And the surviving numbers matched relativity's stretched clock, not the naive prediction. The muon had become a flying test of Einstein, and it passed. Hold on to this idea, because it returns at the heart of the whole story. The faster a muon moves, the longer it lives from our point of view. In the great experiments we are building toward, physicists send muons racing around a ring at that same blistering speed, and relativity stretches their 2 microsecond lives into something like 60 microseconds in the laboratory. That extra time is not a technicality. It is the margin that lets them watch the muon wobble long enough to measure it. So the muon's brief life, which once made it seem useless, becomes a double gift. It is long enough to catch, and it stretches obligingly when the muon runs fast. To use that gift, though, we need to understand the wobble itself. And the wobble begins with the fact that the muon spins. Everything so far has been about what the muon is and where it comes from. Now we turn to the property at the centre of this entire story, the reason a fleeting particle from the sky could ever challenge our deepest theory of nature. The muon behaves like a tiny magnet. You know what a magnet does. Bring a compass near one, and the needle swings to point along the magnet's pull. Set a magnet in the field of another magnet, and it feels a twisting force, lining up or turning until it settles. A magnet has a direction and a strength, and physicists bundle those 2 facts into one idea called the magnetic moment. The magnetic moment is just a measure of how strong a magnet is and which way it points. A powerful bar magnet has a large magnetic moment. A weak fridge magnet has a small one. A muon, absurd as it sounds for something so small, has a magnetic moment too. It is one of the tiniest magnets that can exist. And to see where its magnetism comes from, we start with a picture from ordinary life, then carefully take the picture apart. The everyday picture is this. Magnetism comes from moving electric charge. An electric current looping around a wire makes a magnetic field, which is how an electromagnet works. So imagine the muon as a little ball of charge that is also spinning. A spinning ball of charge is charge going round in a loop, and a loop of charge is a magnet. By that reasoning, any charged particle that spins should act like a small magnet pointing along its spin axis. This picture gets you started, and it gets the direction right. Now here is where the everyday picture gently fails, and the failure matters. The muon is not actually a little ball, and it is not spinning in the way a top or a planet spins. As far as anyone can measure, the muon has no size at all. It is a point. A point cannot literally rotate, because there is nothing off-center to go around, and yet the muon carries a fixed, unchangeable amount of what physicists still call spin, an intrinsic angular momentum that is simply part of what the particle is, like its charge or its mass. Every muon has exactly the same spin as every other. You cannot speed it up or slow it down. It is a built-in property that behaves, in the mathematics, like rotation, and that produces magnetism just as real rotation would. So we keep the useful part of the picture and drop the misleading part. The muon acts like a spinning charge and therefore acts like a magnet, with a definite strength and a definite direction along its spin. But the spin is a deep quantum property that the particle carries for its own reasons, not a physical whirling, and it is only in its effects, like this magnetism, that we can observe it at all. We describe the invisible spin by watching the very visible magnet it creates. That little magnet is the muon's whole role in this story, because if the muon is a magnet, then a magnetic field will grip it and twist it, and the way it responds can be measured with enormous care. The muon becomes a needle we can lay in a field and watch, and the exact strength of that needle, how strong a magnet the muon is for a given amount of spin, is a number that our theories claim to predict with staggering precision. That number has a name. Physicists call it the G factor. It is the ratio between the muon's magnetism and its spin, the single figure that says how strong this particular little magnet is. And the story of the muon mystery is, at heart, the story of a fight over the value of G. The G factor sounds like bookkeeping, but a single number rarely carries as much history as this one does. To feel why physicists cared about it, we go back to 1928 and to one of the strangest minds in the story, Paul Dirac. Dirac was an English physicist known for saying almost nothing. Colleagues told stories about his silences, about answers of a single word, about a man who seemed to think in pure mathematics and found ordinary conversation a waste. Out of that spare and exacting mind came one of the most beautiful equations in physics, an equation that describes how an electron moves when you take both quantum mechanics and Einstein's relativity seriously at once. Before Dirac, those two great theories had not been fully joined for the electron. He joined them. The equation did more than Dirac set out to do, which is the mark of a deep idea. When he worked out what his equation said about an electron sitting in a magnetic field, the magnetism fell out on its own. He had not put the electron's magnet in by hand. The spin and the magnetic moment appeared as necessary consequences of the mathematics, forced by the demand that quantum theory and relativity agree. The electron had to be a little magnet. The equation left no choice, and the equation predicted the exact strength of that magnet. It said the G factor should be precisely 2. To feel the weight of that, consider what a simpler guess would have given. If you pictured the electron as a plain spinning ball of charge, the kind of everyday picture we just set aside, the natural expectation for the G factor would be 1. That is what classical physics, the physics of ordinary spinning objects, suggests, but nature does not use 1. The electron and the muon after it are twice as magnetic for their spin as the naive picture allows. The value is 2, and Dirac's equation delivered that 2 cleanly, from first principles, as if the universe had been waiting for someone to write it down correctly. This was a triumph of the quiet, unanswerable kind. A young man's mathematics had reached into the structure of the electron and pulled out the precise strength of its magnetism a number you could then go and measure. And when experimenters did measure the electron's G-factor in the years that followed, it came out very close to 2, just as Dirac said. The same equation applies to the muon, since the muon is the electron's heavier copy in every way that the equation cares about. For the muon too, the clean prediction is a G-factor of 2. There is a further gift buried in Dirac's work, and it belongs in this part of the story. To make his equation consistent, Dirac found it seemed to describe particles with negative energy, which made no sense on its face. Rather than throw the puzzle out, he followed the mathematics and proposed that these corresponded to a partner particle, identical to the electron but with opposite charge. That was the positron, antimatter, and it was exactly the particle Carl Anderson stumbled on in his cloud chamber a few years later, the same Anderson who would then go on to find the muon. The threads of this story keep tying back to one another, so by the early 1930s, physics held a crisp and confident prediction. The G-factor of these particles is 2, not a shade more, not a shade less. 2, exactly, forever. That confidence lasted about 20 years. Then a closer look revealed that the G-factor is not exactly 2 after all. It is a tiny bit larger, and that tiny excess, that small overflow past the perfect number, is the crack through which the whole modern mystery pours. The overflow has a name. It is called the anomaly. After the Second World War, physics came back to a problem it had shelved. Dirac's equation said the G-factor was exactly 2, and measurements said it was close to 2, but perhaps not exact. The instruments were getting good enough to tell the difference, and a small discrepancy was creeping in. The electron seemed to be very slightly more magnetic than a clean 2 would allow. The man who explained it was Julian Schwinger, an American physicist so precocious he had published research as a teenager and lectured at a blackboard with the polish of a performance. In 1948, Schwinger worked out where the extra magnetism came from, and his answer opened the door to everything that follows. The key idea is that an electron, or a muon, is never truly alone. Around every charged particle there is a haze of activity, a constant flicker of other particles winking in and out of existence too briefly to catch directly. We will look closely at that haze in a moment. What matters here is that this flicker slightly changes how the particle responds to a magnetic field. It nudges the G-factor upward, a hair past 2. Schwinger calculated the size of that first nudge, and it came out to a specific small number. The G-factor should exceed 2 by about 1 part in 800. Physicists write the size of the overflow with a single symbol, the letter A, and they call it the anomaly. The anomaly is defined as the amount by which G runs past 2, cut in half, so that a clean Dirac value of 2 would give an anomaly of 0. Schwinger's calculation said the anomaly is, to first approximation, a certain famous constant divided by 2 times pi, worked out as a decimal that is roughly 0.00116. A tiny overflow, about 0.1% added onto the magnetism. And when experimenters measured the electron's anomaly, it matched Schwinger's number. That match was a founding moment for the theory we now call quantum electrodynamics, the theory of how light and charged particles interact, usually shortened to QED. Schwinger, along with Richard Feynman and the Japanese physicist Sin Itaro Tomonaga, built quantum electrodynamics into a working machine in these post-war years, and the three of them would share a Nobel Prize for it. It became the most precisely tested theory in the history of science, and its very first triumph was explaining why the G-factor is not quite 2. Schwinger was so proud of this result that he had the formula for it carved on his headstone. the little expression for the anomaly, the constant over 2π, marks his grave. It is one of the few equations you can visit. Now notice what this has done to the whole enterprise. Before Schwinger, the G-factor was a single clean prediction, 2, and there was nothing more to say. After Schwinger, the G-factor became a layered thing. There is the plain Dirac value of 2, and then a series of ever smaller corrections stacked on top, each one from the flickering haze around the particle, each one calculable if you work hard enough. The first correction is Schwinger's. Beyond it are smaller ones, and smaller ones still, a descending staircase of refinements. Every one of those corrections is a place where nature could hide a surprise. Because the corrections come from every kind of particle that can flicker around the muon, the total anomaly is, in effect, a sum over everything that exists. If some particle is missing from our list, the muon's anomaly will come out slightly wrong. That is the whole reason this measurement can hunt for hidden things. To understand how, we have to look directly into that flickering haze. We have to talk about the vacuum, and about the fact that empty space is not empty. Empty space seems like the simplest thing in the world. Take a box, remove the air, remove the light, remove every particle, and you have a vacuum, a region of pure nothing. That is the everyday picture, and it is wrong in a way that turns out to be central to our story. According to quantum theory, the vacuum is not still. It churns. On the tiniest scales of space and the shortest slivers of time, particles are constantly appearing in pairs and vanishing again, borrowing energy from nothing and paying it back before the universe can notice. A particle and its antiparticle bubble up together, exist for the briefest instant, and annihilate. This happens everywhere, all the time, throughout what we call empty space. The vacuum is less like an empty room and more like the surface of a pot just before it boils, trembling with fleeting activity. These fleeting particles are called virtual particles. The word virtual is a warning. They are not quite real in the way the muon is real, because they never last long enough to be caught on their own. But their effects are real and measurable, and the muon's anomaly is one of them. Here is how they touch the muon. As the muon travels through a magnetic field, it is not a bare point of charge. It is wrapped in a shimmering cloud of these virtual particles, constantly flickering into being around it and dissolving away. The muon might briefly emit a virtual photon, a fleeting bundle of light, and reabsorb it. Or that virtual photon might, for an instant, turn into a virtual electron and positron pair, which then recombine. The muon is dressed at every moment in a cloud of borrowed particles, and that cloud slightly alters how it feels the magnetic field. The dressing changes the wobble. That is the origin of Schwinger's correction and every correction after it. Richard Feynman gave physicists a way to draw and count these possibilities in the little pictures now called Feynman diagrams. Each diagram is a cartoon of one thing that can happen in the cloud, one way the muon can flicker and interact on its way through the field. The simplest diagram gives Schwinger's first correction. More elaborate diagrams, with more virtual particles doing more complicated things, give smaller and smaller corrections. To predict the muon's anomaly to high precision, physicists add up thousands upon thousands of these diagrams, each contributing its tiny share to the total. Now, the reason this measurement can hunt for the unknown comes into focus. The cloud around the muon can contain any particle that exists and that the muon can interact with. Familiar particles, the electron, the photon, the quarks, all take their turn flickering in the haze. But if there is some particle we have never seen, some new heavy thing tied to a force we have not yet discovered, it too would occasionally flicker in that cloud. it would add its own small contribution to the anomaly. And so the measured value of the muon's anomaly is a kind of census. It counts everything that can dress the muon, seen and unseen. If the census comes out slightly higher than our list of known particles predicts, the excess is a sign that something is out there, contributing from the shadows. This is the deep reason the muon's wobble became a search for hidden physics. You are not looking at the new particle directly, you are looking at the muon and reading, in the exact strength of its magnetism, the faint fingerprints of everything that has ever touched it, including things you cannot yet name. Which raises an obvious question. If both the electron and the muon carry this same kind of cloud, why chase the muon, a fragile particle from the sky, instead of the stable, convenient electron? The answer is mass. If you wanted to weigh the influence of unknown particles, you might expect the electron to be the ideal tool. It is stable, it sits still in traps for months, and physicists have measured its anomaly to more decimal places than almost any other quantity in nature. So why does the search for hidden forces ride on the muon, which lives 2 microseconds and must be caught on the fly? The reason is that the muon is heavy, and heaviness here means sensitivity. Recall the cloud of virtual particles that dresses every charged particle. Some of those virtual visitors are light, like the electron and the photon. Others, if they exist, would be heavy, like the undiscovered particles that new forces might bring. A key fact about this cloud is that a particle's sensitivity to heavy virtual visitors grows with its own mass. The heavier the particle at the centre, the more strongly the heavy members of the cloud make themselves felt in its anomaly. The rule of thumb is sharper than that, and it is worth stating plainly. The effect of a heavy new particle on a lepton's anomaly scales with the square of the lepton's mass. The muon is about 207 times heavier than the electron. Square that, and you get somewhere around 40,000. So the muon is roughly 40,000 times more sensitive than the electron to the influence of heavy, unknown particles flickering in its cloud. A hidden force that nudges the electron's anomaly by an amount far too small to ever detect would nudge the muon's anomaly by 40,000 times as much, into a range where careful experiments have a real chance of seeing it. That single fact is why the muon, and not the electron, sits at the centre of this hunt. The electron's anomaly is a magnificent test of quantum electrodynamics, of the light and familiar part of the cloud, and it passes that test to a dozen decimal places. But the electron is nearly deaf to heavy newcomers. The muon is the one that listens for them. It trades the electron's stability for a far keener ear. Think of it as the difference between 2 microphones. The electron is a fine microphone, tuned to the ordinary sounds of the room, and it reproduces them with breathtaking fidelity. The muon is a special microphone built to pick up a deep, distant rumble that the first one cannot hear at all. If there is a low note out there in the structure of nature, a heavy particle no one has catalogued, the muon is the instrument that might register it. The tau, heavier still, would be an even better microphone, but it decays far too fast to place in any ring and watch. The muon is the heaviest lepton we can actually hold long enough to listen to. This is the quiet reason the particle nobody ordered became indispensable. Its uselessness in ordinary matter and its inconvenient short life are beside the point. What matters is that its heaviness makes it a natural detector for exactly the kind of new physics that lies just out of reach, the heavy particles that might belong to forces beyond the ones we know. The muon is a probe that nature handed us, tuned to the frequencies we most want to hear. But a probe is only as good as your ability to read it, and here the 2 halves of the story come together. To use the muon's sensitivity, you need 2 things, each pushed to an extreme. you need a prediction of its anomaly so precise that it accounts for every known particle in the cloud down to many decimal places. And you need a measurement of its anomaly equally precise, so that any gap between them stands out clearly. If the two agree, the known particles are the whole story. If they disagree, something is hiding in the muon's cloud. The prediction side rests on one number that appears again and again, and it deserves a chapter of its own. Every prediction of the muon's anomaly leans on a single constant of nature, a number that measures how strongly light and charged particles pull on one another. It is called the fine structure constant, and it is one of the most important numbers in physics. The fine structure constant sets the strength of the electromagnetic force. When two charged particles push or pull, when a muon emits a virtual photon into its cloud, the vigour of that interaction is governed by this one figure. Physicists write it with the Greek letter alpha. Its value is close to 1 divided by 137. That is a small number, and its smallness is a kind of mercy, because it is the reason the cloud of virtual particles can be handled at all. Here is why the smallness matters. Each layer of the cloud, each more elaborate flickering, contributes less than the layer before, and the shrinking factor from one layer to the next is roughly this fine structure constant. Because alpha is about 1 part in 137, each successive correction is around 100 times smaller than the one before it. Schwinger's first correction is the largest. The next layer is far smaller. The one after that, smaller still. The staircase descends quickly. That steep descent is what lets physicists calculate the anomaly to extraordinary depth. They can compute the first correction, and the second, and the third, and the fourth, each requiring monstrous effort, and know that the uncomputed remainder is too small to matter yet. For the electron, this program has been carried out to a level that is hard to comprehend. The electron's anomaly has been calculated and measured and found to agree to about 12 digits. 12 digits of agreement between a pencil and paper theory and a laboratory measurement. To picture what that means, imagine measuring the distance from New York to Los Angeles and having your prediction and your measurement agree down to the width of a human hair. That is the kind of precision quantum electrodynamics reaches for the electron, and it is why physicists trust the theory so deeply. It is the most stringently tested theory humanity has ever built, and it holds. The value of alpha itself is measured in its own clever ways, not taken from the anomaly, so the whole scheme is a genuine test rather than a circular one. You pin down the fine structure constant by other experiments, feed it into the calculation of the anomaly, and compare with the measured anomaly. When the two match to a dozen digits for the electron, you know the machinery is sound. Now bring the muon back in. The muon's anomaly is built from the same fine structure constant, the same descending staircase of corrections, the same quantum electrodynamics that works so flawlessly for the electron. That part of the muon's prediction, the pure electromagnetic part, is known with the same superb precision, calculated through many layers of the cloud. If the muon felt only electromagnetism, its anomaly would be predicted and measured to a dozen digits, and there would be no mystery. But the muon's cloud has more in it than electromagnetism. Because the muon is heavy, other forces reach into its cloud with enough strength to matter. The weak force, which governs certain kinds of radioactive decay, adds its small contribution. And the strong force, the very force the muon was once mistaken for carrying, reaches in as well through virtual particles made of quarks. Those extra contributions are far harder to pin down than the clean electromagnetic ones, and they are where the real difficulty of predicting the muon's anomaly lies. We will face that difficulty directly when the time comes. First though, We have followed the prediction as far as plain reasoning takes us. It is time to cross to the other side of the contest and ask how anyone measures the muon's magnetism in the first place. It begins with a ring. How do you measure the strength of a magnet you can never see, a magnet a fraction the size of an atom that lives for 2/millionths of a second? You cannot lay it against a ruler or hang it from a scale. What you can do is set it spinning in a magnetic field and watch how it wobbles. The wobble carries the number you want. Start with the spinning top again, because it is the truest everyday guide. Set a top spinning on a table and it does not stay perfectly upright. Its axis leans and slowly circles around the vertical, tracing a cone, while the top keeps spinning fast underneath. That slow circling of the axis is called precession. Gravity is trying to tip the top over, the top's own spin resists, and the compromise between them is this steady wheeling of the axis around. A muon in a magnetic field does something very similar, but the field takes the place of gravity. The muon is a little magnet with a spin, and when you place it in a magnetic field, the field grips its magnetism and tries to twist it into alignment, while the muon's spin resists. The result is that the muon's spin axis precesses, wheeling steadily around the direction of the magnetic field, just as the top's axis wheels around the vertical. And here is the crucial link. How fast the spin precesses depends directly on how strong a magnet the muon is, which is to say, on its G-factor. A stronger magnet precesses faster. Measure the rate of the wobble, and you have measured G. So the plan, in outline, is to get muons into a magnetic field, keep them there, and clock how fast their spins wheel around. To keep fast-moving muons in one place long enough to watch, physicists send them in a circle. They build a great ring, thread a magnetic field through it, and inject muons to race around the loop again and again, held on their circular path by the same field that makes them precess. A storage ring, it is called, because it stores the particles in circulation. Now a subtlety enters, and it is the clever heart of the method. As a muon circles the ring, two things are turning at once. The muon's direction of motion swings around the circle, once per lap, and the muon's spin precesses wheeling around at its own rate. If those two rates were identical, the spin would always point the same way relative to the muon's motion, and you would learn nothing about any overflow past 2. But they are not identical, and the mismatch is exactly the point. If the G-factor were precisely 2, the spin would turn just slightly faster than the motion, in a simple relationship. The tiny extra magnetism from the anomaly, the overflow we have been chasing, makes the spin creep ahead of the motion a little more. What physicists actually measure is the difference between the two turning rates, the rate at which the spin gains on the direction of travel. That difference frequency is small, and beautifully it depends only on the anomaly, on the overflow past 2, and not on the clean part. The experiment is built to measure precisely the thing in dispute, the little excess, and to set aside the large, uninteresting bulk. This is why the whole enterprise is so sensitive. You are not measuring a G-factor of 2 and hoping to see a wobble in the 12th decimal place. You are measuring only the overflow, directly as a slow drift of the muon spin against its own motion around the ring. The large number 2 never enters, only the anomaly does. To make even that difference clean, though, the experimenters need one more trick, a special speed at which a stubborn source of error simply disappears. They call it the magic momentum. A storage ring has a practical problem. The magnetic field bends the muons around the loop, but it does not, on its own, keep them from drifting up or down, wandering out of the beam. To hold the muons vertically in place, the experimenters need electric fields, electric focusing plates that gently push stray muons back toward the center of the beam pipe. And here a danger appears. Electric fields, like magnetic fields, can twist a moving magnet's spin. If the focusing fields disturb the muon's precession, they corrupt the very measurement you are trying to make. For most speeds, this would be a serious contamination. The electric focusing needed to keep the beam together would add an unknown twist to the spin, and you could never cleanly separate the magnetic wobble you want from the electric nuisance you do not. It looks, at first, like a fatal flaw in the whole scheme. There is a way out, and it is one of the most elegant tricks in experimental physics. It turns out that the electric field's effect on the spin precession depends on how fast the muon is moving, and that this effect changes sign as the speed changes. At low speeds it pushes the precession one way, at high speeds it pushes the other way. Somewhere in between there is a single special speed at which the electric field's twist on the precession exactly cancels out, and the muon's spin wheels around as if the focusing plates were not there at all. At that one magic speed, the electric fields hold the beam together without disturbing the measurement. That special speed corresponds to a particular momentum, and physicists call it the magic momentum. Its value is about 3 billion electron volts in the units particle physicists use, a shorthand for how much energy the muon carries. At that momentum, the muon is moving at roughly 99.94% of the speed of light. So the muons in the ring are not merely fast. They are threading a needle launched at one precise speed where a whole category of error vanishes. This is the kind of gift that makes an impossibly hard measurement merely very hard. By choosing the magic momentum, the experimenters remove the electric fields from the equation almost entirely, and the difference frequency they measure comes to depend, to very good approximation, on just two things. It depends on the strength of the magnetic field, which they can map out with great care. And it depends on the muon's anomaly, the overflow past 2, which is the number they are after. Clean the field measurement, count the wobble, and out comes the anomaly. It is worth pausing on how demanding this is. The muons must be produced, selected, and injected into the ring at that exact magic momentum, which means building an accelerator complex upstream that delivers muons at just the right speed. The magnetic field around the entire ring must be known to extraordinary uniformity, because any lump or dip in the field would shift the wobble and fake a false anomaly. Teams spend years mapping and smoothing the field, a process called shimming, adjusting thin pieces of metal around the ring until the field is even to a few parts in a million all the way around. The whole machine is a monument to controlling one number, the field, so that another number, the wobble, can be read without doubt. And the magic momentum quietly hands the experiment one more advantage, the very one we met earlier with cosmic rays. A muon moving at 99.94% of light speed has its brief life stretched by relativity. The 2 microsecond muon, running that fast, survives many times longer in the laboratory, long enough to circle the ring hundreds of times and let its spin drift measurably against its motion. Relativity, once again, buys the time the experiment needs. That stretched life is worth a closer look, because without it, none of this would be possible. We have already seen relativity save the muon once, high in the atmosphere, where time dilation lets cosmic ray muons reach the ground instead of dying in the upper air. In the storage ring, the very same effect returns, and this time physicists put it deliberately to work. Without it, there would be nothing to measure. Consider the raw numbers. A muon at rest lives about 2.2 microseconds before it decays. In the ring, the muon is not at rest. It is circling at the magic momentum at 99.94% of the speed of light, and at that pace its internal clock, seen from the laboratory, runs far slower than yours. The stretch factor at this speed is close to 30. So the muon's lifetime, which is a little over 2 microseconds when it sits still, balloons to something around 64 microseconds as it races around the ring. It lives in the laboratory's reckoning roughly 30 times longer than it otherwise would. 64 microseconds is still a flicker by human standards, but for the experiment it is a windfall. In that stretched lifetime, a muon can complete hundreds of laps around the ring. Each lap its spin creeps a little further ahead of its direction of motion, the anomaly slowly revealing itself through the accumulating drift. The more laps the muon survives, the more precisely that slow drift can be measured. Relativity, by stretching the muon's life 30-fold, gives the experiment hundreds of turns where a still muon would have allowed only a handful. The margin between a measurement and no measurement at all is written in Einstein's stretched clock. There is something quietly wonderful in this. The experiment is designed to test our deepest theory of particles, and to even take place. It depends on another of physics' great theories working exactly as advertised. Relativity is not being tested here. It is simply assumed, trusted and leaned on, its time dilation folded into the machinery as a reliable tool. Every muon that survives long enough to be counted is, in passing, one more confirmation that time really does slow for the swift. But nobody in the control room thinks of it that way anymore. Relativity has become plumbing. The stretched lifetime also shapes how the data comes in. Because the muons decay throughout their extended life, they do not all vanish at once. They fall away gradually, some decaying after a few laps, some after many, the population thinning smoothly as the microseconds pass. Over the whole run, the number of muons still circling drops off in the steady curve of radioactive decay, halving again and again. The experimenters watch this dwindling crowd, and as it dwindles, they track the wobble of the spins that remain. The measurement is a race against the muon's disappearance, and relativity is what keeps the race long enough to finish. This dependence on stretch time is also why the magic momentum was chosen as high as it was. A slower muon would not only reintroduce the electric field problem we just cleared away, it would also live a shorter time in the laboratory, decaying too soon to give many laps. The high speed does double duty. It cancels the electric contamination and it stretches the life. The two blessings arrive together at the same magic momentum, which is part of why that particular speed is so prized. So the ring holds a crowd of muons, born at the magic momentum, circling hundreds of times in their relativistically stretched lives, spins slowly drifting ahead of their motion. Everything is now in place except the reading itself. How does anyone actually see which way a muon spin is pointing from outside the beam pipe without ever touching the muon? The answer lies in the way the muon dies, and in a deep asymmetry built into the weak force. Everything now depends on a single question. As a muon circles the ring, its spin slowly wheeling around, how can anyone standing outside possibly tell which way that spin points? You cannot see a spin, you cannot photograph it, and yet the whole measurement requires reading the spin's direction over and over as the muons circle. The answer is hidden in the way the muon dies. Two facts make it work, and both come from the weak force, the same force behind certain kinds of radioactive decay. The first fact concerns the muon's birth. The muons are made from decaying pions, and because of a deep property of the weak force, the muons come out already spinning in a known direction relative to their motion. They are born aligned, or polarized, all their spins pointing the same way to start. The experiment does not have to arrange this. Nature hands over a beam of muons already marching in step. The second fact concerns the muon's death, and it is stranger. When a muon decays, it emits an electron, or for the positive muons often used, a positron, along with the ghostly neutrinos. You might expect that decay particle to fly off in any direction at random. It does not. Because of an asymmetry in the weak force, the decay tends to fling its electron or positron preferentially along the direction the muon's spin is pointing. The muon, as it dies, throws its decay particle mostly in the direction of its own spin. This asymmetry has a name and a history. It is called parity violation, and its discovery in the 1950s, guided by the theorists Songdao Li and Chen-Ning Yang, and demonstrated in the laboratory by the physicist Chen-Sheng Wu, overturned a cherished assumption that nature treats left and right the same. It does not. The weak force can tell left from right, and one consequence is this lopsided decay, the decay particle leaning toward the muon's spin. What was once a shocking violation of expectation is now the reliable tool that makes the whole measurement readable. Put the two facts together and the method appears. The muons circle the ring, their spins slowly wheeling around as they precess. Whenever a muon decays, it fires its positron mostly in the direction its spin happens to point at that instant. Detectors line the inside of the ring, waiting to catch those positrons. So as the spins wheel around, the positrons come flying out in a direction that wheels around with them. When the spins point toward the detectors, more positrons strike them. When the spins point away, fewer do. The count of positrons rises and falls in step with the precessing spins. The result, when the experimenters plot how many positrons arrive over time, is one of the most iconic pictures in physics. The overall number of positrons falls away steadily as the muons decay and the crowd thins, the smooth downward slope of radioactive decay. But riding on top of that falling curve is a gentle ripple, a rising and falling wiggle, as the wheeling spins sweep the positron spray toward and away from the detectors, again and again. Physicists simply call it the wiggle plot. The rate of the wiggle is the difference frequency we have been chasing all along, the rate at which the spins gain on the muon's motion. And that frequency, as we saw, gives the anomaly directly. So the invisible spin is read through the visible spray of decay particles. Nobody ever sees a muon spin. They see the wiggle in the positron count, and from the tempo of that wiggle they extract the overflow past 2, the muon's anomaly, to many decimal places. The chain is complete, from the muon's polarized birth, through its stretched circling life, to its lopsided death caught by the detectors. This method did not spring into being fully formed. It was built up over decades, and the first place it was carried to real precision was not in America, but in Europe, at a laboratory whose early muon experiments quietly confirmed Schwinger and set the stage for everything after. Before the great rings in America, there was a series of experiments in Europe at the laboratory called CERN, on the border between France and Switzerland. Through the 1960s and into the 1970s, physicists there measured the muon's anomaly 3 times over, each attempt sharper than the last, and in doing so they built the method we have just described and proved that it worked. The first CERN muon experiment, in the early 1960s, was modest by later standards, but it did something no one had done before. It measured the muon's anomaly directly, the overflow past 2, and found it in agreement with the prediction from quantum electrodynamics. Schwinger's correction, the little excess from the cloud of virtual particles, was confirmed not just for the electron but for its heavier cousin. The muon was magnetic by just the amount the theory said, to the precision then available. The second CERN experiment brought in the storage ring in earnest, sending muons around a magnetic loop and watching the wiggle in their decay. The precision improved, and still the measurement matched the theory. By now, the corrections being tested were not only Schwinger's first term, but the smaller terms beyond it, the second and third layers of the descending staircase. Quantum electrodynamics predicted those finer corrections, and the muon obeyed them. Each improvement in the experiment was a chance for the theory to fail, and each time it held. The third CERN experiment, running into the 1970s, is the one that matters most for our story, because it was precise enough to feel the strong force. Recall that the muon's cloud contains not only photons and electrons, but also, faintly, virtual particles made of quarks, the stuff of the strong force. Those strong force contributions to the anomaly are small, but by the third experiment the measurement had become sharp enough that they could no longer be ignored. For the first time, the muon's anomaly was measured well enough to see the imprint of the strong force in its magnetism. The prediction now had to include that harder, messier piece, and when it did. Prediction and measurement still agreed. This was a quiet turning point that many tellings of the muon story skipped past on their way to the American experiments. The CERN work is where the muon's anomaly graduated from a test of quantum electrodynamics alone into a test of the whole standard model, strong force and all. It is also where physicists first ran into the difficulty that would come to dominate everything. The clean electromagnetic corrections could be calculated to as many digits as anyone had patience for. The strong force contribution could not. It resisted. It carried an uncertainty that the tidy electromagnetic part never did, and that uncertainty would grow into the central obstacle of the modern era. The CERN experiments ended with prediction and measurement in agreement within the precision of the day. There was no anomaly beyond the expected one, no hint of hidden forces. But the precision of the day was the limit. To go further, to reach the level where a genuinely new particle might reveal itself in the muon's cloud, both sides would have to improve by a large factor. The measurement would need many more muons and far better control of the magnetic field. The prediction would need a much sharper handle on that stubborn, strong force piece. That next leap moved across the Atlantic to a laboratory on Long Island, where a new ring was built to push the muon's anomaly to a precision the CERN teams could only dream of. And when that experiment finally reported its number, near the turn of the century, it did not agree with the prediction. For the first time, a real gap opened between what the muon did and what the theory said it should do. The whisper had begun. The new experiment sat at Brookhaven National Laboratory on Long Island in New York, and it went by the name E821. Its heart was a storage ring far larger and more refined than anything at CERN, a superconducting magnet 50 feet across, about 15 meters, cooled to hold a strong and exquisitely uniform field. Through the late 1990s and into 2001, this ring gathered muons by the billion, watched their spins wheel around, and pushed the measurement of the anomaly to a precision several times finer than the European work. The idea was the same one built up at CERN. Inject polarized muons at the magic momentum, let them circle in their relativistically stretched lives, and read the wiggle in the decay positrons to extract the overflow pass too. What was new was the scale and the care. The Brookhaven team mapped their magnetic field to a few parts in a million all the way around the ring, shimming it for years, counting positrons until the statistical noise fell low enough to see the anomaly in more decimal places than ever before. When the result came in, it did not match the prediction. The muon's measured anomaly came out slightly larger than the standard model said it should be. The gap was tiny in absolute terms, a difference in a distant decimal place, but it was there, and it was stubborn. As the Brookhaven team refined their number and the theorists refined theirs, the two would not converge. The measurement sat a little above the prediction and stayed there. Physicists measure the seriousness of such a gap in units called standard deviations, or sigma. 1 sigma is roughly the ordinary size of the expected wiggle in a measurement. The amount two numbers might differ by pure chance. A gap of 1 or 2 sigma is nothing to lose sleep over, the kind of near miss that random variation throws up all the time. A gap of 3 sigma is worth attention. 5 sigma is the traditional threshold for claiming a discovery, the point at which chance becomes an implausible explanation. The Brookhaven gap hovered around 3 sigma. Not a discovery, but not nothing. Too large to shrug off, too small to trust completely. 3 sigma is the most tantalizing place a result can sit. It is enough to make you wonder whether you are seeing the edge of something real. A new particle flickering in the muon's cloud and nudging its magnetism upward. It is also small enough that a subtle flaw in the experiment or in the fiendishly hard prediction could account for the whole thing. For years the Brookhaven anomaly lived in exactly that limbo. Every seminar on physics beyond the standard model would mention it. Every theorist with an idea for a new particle would check whether it could explain the muon. And no one could say for certain whether the gap was a message from nature or a mistake in the arithmetic. The obvious next step was to measure again, better, but Brookhaven had pushed its ring about as far as it could go. To shrink the experimental uncertainty by the needed factor would take far more muons, a more intense beam, and years of new data. Brookhaven no longer had the accelerator complex to deliver that. Another laboratory did. So the Brookhaven era ended with a gap that would not close and could not be resolved. The muon was wobbling a hair faster than the rulebook allowed, and nobody knew why. The measurement needed to be redone at a scale Brookhaven could not reach, and the prediction needed to be sharpened on its hardest piece. The strong force contribution that had troubled the field since CERN. Before we follow the ring on its long journey to a new home, we should understand what the prediction actually contains, and why one part of it is so much harder than the rest. The standard model's answer for the muon is a sum of 3 pieces, and 2 of them are beautifully clean. The standard model's prediction for the muon's anomaly is not one calculation, but a sum of 3, one for each of the forces that reach into the muon's cloud. 2 of those pieces are known with superb precision. The third is the source of nearly all the trouble. To see where the mystery really lives, it helps to take the 2 clean pieces first and admire how well they are understood. The largest piece by far comes from electromagnetism, from quantum electrodynamics, the theory of the muon trading virtual photons and light particles in its cloud. This is the part built on the fine structure constant and the descending staircase of corrections we met earlier. It is Schwinger's term, plus the smaller term beyond it, plus the smaller one beyond that, computed layer after painstaking layer. Physicists have pushed this calculation to 5 layers deep, an achievement of almost monastic labour, with the deepest layers requiring vast computer, runs over thousands of contributing diagrams. The electromagnetic piece accounts for all but a whisker of the muon's anomaly, and it is known to more decimal places than the experiment can currently test. If the muon felt only electromagnetism, prediction and measurement would agree perfectly, and there would be no story. The second piece comes from the weak force, the force behind certain radioactive decays, and the same force that gives the muon its polarized birth and lopsided death. Heavy particles associated with the weak force can flicker briefly in the muon's cloud. The particles called the W and the Z, along with the Higgs. Because these particles are so heavy, they are reluctant to appear even virtually, so their contribution to the anomaly is small, far smaller than the electromagnetic part. But it is not zero, and crucially, it is calculable. The masses of the weak force particles are well measured, the theory is well understood, and the electroweak contribution to the muon's anomaly is known cleanly and confidently. It is a small, firm number, so 2 of the 3 pieces are under control. The electromagnetic piece is enormous and known to exquisite precision. The electroweak piece is tiny and known reliably. If those were the whole story, the standard model would hand over a prediction for the muon's anomaly as sharp as the one for the electron, and any gap with experiment would be a clean signal of something new. The muon would be a straightforward messenger. The third piece ruins that simplicity. It comes from the strong force, the force that binds quarks into protons and neutrons, and it enters the muon's cloud through virtual particles made of quarks. This strong force contribution is small, comparable in size to the electroweak piece, small enough that in a simpler world it would hardly matter. But it cannot be calculated the way the other 2 can. The strong force does not obey the tidy descending staircase. Its corrections do not shrink politely from one layer to the next. At the low energies that matter here, the strong force is fierce and tangled, and the usual method of adding up diagrams simply fails. The strong force piece is where all the uncertainty in the prediction collects. This is the pivot of the entire modern mystery. The Brookhaven gap and the Fermilab gap after it were never about the electromagnetic or electroweak pieces, which everyone trusts. They were about whether the strong force piece had been calculated correctly. A gap between prediction and measurement could mean a hidden new particle in the muon's cloud, or it could mean the strong force contribution had been gotten slightly wrong. Those 2 explanations look identical in the final number, and telling them apart has consumed the field for a quarter of a century. To understand why the strong force piece is so hard, and why it splits into 2 rival methods that would eventually disagree with each other, we have to look at what quarks do inside the muon's cloud. The strong force contribution to the muon's anomaly has a specific name, and it is worth learning, because it sits at the exact centre of the puzzle. It is called hadronic vacuum polarization. The word hadronic means having to do with particles made of quarks, like protons, neutrons, and the lighter particles called pions. The phrase describes one particular thing that can happen in the muon's cloud, and once you can picture it, the whole difficulty comes into focus. Here is the picture. As the muon moves through the magnetic field, it emits a virtual photon, a fleeting bundle of light, as it does countless times. Usually that virtual photon simply flickers and is reabsorbed. But sometimes, on its brief journey, the photon does something richer. It turns for an instant into a pair of quarks, a quark and an antiquark, which immediately bind into short-lived hadrons before recombining back into the photon. For that instant, the muon's cloud contains not just light and electrons, but a tiny storm of strongly interacting matter, quarks flickering in and out. That momentary appearance of hadronic matter in the cloud is hadronic vacuum polarization, and it makes its own small contribution to the muon's magnetism. The trouble is calculating how large that contribution is. For the electromagnetic cloud, the interactions are gentle enough that the descending staircase works, each layer smaller than the last. The strong force is not gentle. At the low energies where these virtual quarks live, the strong force is overwhelmingly powerful, so powerful that quarks can never be pulled apart and studied alone. They are locked inside hadrons, and when a force is that strong, the usual trick of adding up a shrinking series of corrections collapses. The corrections do not shrink. The whole tidy method that makes quantum electrodynamics so precise simply does not apply to the strong force at these energies. This is not a small technical annoyance. It is a fundamental wall. The strong force described by the theory called quantum chromodynamics is understood in principle, its equations written down decades ago. But solving those equations in the regime that matters for the muon, where the force is fiercest, has resisted every straightforward approach. You cannot just compute hadronic vacuum polarization from the equations with pencil and paper the way you compute Schwinger's term. The math will not cooperate. So the strong force piece became the single largest source of uncertainty in the entire prediction, even though it is one of the smallest contributions by size. A small number known poorly can dominate the error budget. And it does. When physicists quote the uncertainty in the standard model prediction for the muon's anomaly, they are quoting almost entirely the uncertainty in hadronic vacuum polarization. Everything else is nailed down. This one piece wobbles. And that means the whole comparison hinges on it. If the true value of hadronic vacuum polarization is a little larger than physicists thought, the prediction rises, and the gap with experiment shrinks or vanishes. If it is a little smaller, the prediction falls, and the gap grows, and the case for a hidden new particle strengthens. The entire question of whether the muon is pointing at new physics comes down to getting this one stubborn strong force number right. Faced with a wall, physicists found two different ways around it. Two independent methods for pinning down hadronic vacuum polarization without solving the impossible equations head-on. One method borrows from real experimental data, the other simulates the strong force on a computer. For years they seemed to agree well enough. Then, at the worst possible moment, they began to disagree with each other, and the muon mystery turned into something no one expected. A quarrel not between experiment and theory, but between two theories. Since the strong force piece cannot be calculated directly, physicists developed two independent roads to it, and the story of the last few years is largely the story of these two roads pulling apart. Understanding both is the key to everything that follows, so let us walk each one in turn. The first road is called the data-driven method. Its insight is clever. The same tangle of virtual quarks that appears in the muon's cloud also appears, in a related form, in a process you can actually measure in a laboratory. If you collide electrons and positrons at the right energies, they annihilate into a virtual photon, and that photon turns into real hadrons, real particles made of quarks, that fly out and strike detectors. Physicists have measured the rate of this process, electrons and positrons turning into hadrons across a wide range of energies, in many experiments over many years. And there is a deep mathematical relationship worked out long ago that lets you convert those measured rates into the value of hadronic vacuum polarization. You do not calculate the strong force. You measure a cousin process in the real world and let the data tell you the answer. For decades, this was the gold standard. The data-driven method used real measurements, so it sidestepped the impossible calculation entirely, and it gave a value for hadronic vacuum polarization with a stated precision good enough to matter. When the international team called the Muon G-2 Theory Initiative gathered the world's best estimate in 2020, they leaned on this data-driven road. That 2020 prediction is the one the Brookhaven and early Fermilab measurements were compared against, and it sat below the measurement, giving the tantalizing gap. The second road is called lattice quantum chromodynamics, or lattice QCD. Its approach is brute force of a beautiful kind. Since you cannot solve the equations of the strong force with pencil and paper, you solve them numerically on a supercomputer. You imagine space-time not as smooth but as a fine grid, a lattice of points. And you compute the behaviour of quarks and gluons at every point on that grid, then let the grid grow finer and finer to approach the real continuous world. It is staggeringly demanding, requiring some of the largest computers on Earth running for months, but it is a genuine calculation from first principles, using only the fundamental equations and no experimental input about hadrons at all. For a long time, lattice QCD was not precise enough to compete. Its uncertainty on hadronic vacuum polarization was too large to test the muon gap. But the method improved steadily, year after year, as computers grew and techniques sharpened, until finally it reached the precision needed to weigh in. And here is the crucial point. The two roads are completely independent. The data-driven method uses real collision data and a mathematical relationship. Lattice QCD uses only the fundamental equations and a supercomputer. They share no assumptions. If both are done correctly, they must give the same answer, because they are computing the same physical quantity by different means. So the stage was set for a powerful cross-check. Two independent roads to the one stubborn number that decided whether the muon was pointing at new physics. If they agreed, and both sat below the measurement, the case for a hidden force would be strong. If they agreed and sat at the measurement, the case would collapse. Nobody seriously expected the third possibility, the one that actually happened, which was that the two roads would disagree with each other, and the muon mystery would fracture into a deeper puzzle about which theoretical method to trust. That fracture was still a few years off. First, the measurement itself had to be redone, and that meant moving a 15-metre superconducting magnet across a continent without letting it flex more than the width of a few coins. When Brookhaven's ring reached the end of what it could measure, the magnet did not retire. It moved. Fermilab, outside Chicago in Batavia, Illinois, had the intense muon beam needed to gather far more data. But building a new ring of the required precision would have cost enormous time and money. The Brookhaven ring already existed, already tuned to a superbly uniform field after years of shimming. The obvious plan was to bring the ring to the beam. The catch was that the ring lay on Long Island, and Fermilab lay more than 3,000 miles away by the only route the ring could survive. The difficulty was the magnet's fragility. The ring is a single circular structure of superconducting coils, 15 meters across, and its delicate electrical connections cannot bend. If the ring flexed by more than a few millimeters, a fraction of an inch, the coils could be permanently damaged and the whole instrument ruined. You could not disassemble it and rebuild it, because the assembly itself was part of what made the field so uniform. The ring had to travel in one piece, held nearly perfectly flat the entire way. That ruled out most direct routes. You cannot drive a rigid 15-meter circle over the potholes and hills of 3,000 miles of highway without flexing it. So the planners chose water. In the summer of 2013, the ring was wrapped, mounted on a special support structure, and floated onto a barge. It travelled down the east coast of the United States by sea, around the tip of Florida into the Gulf of Mexico, and then up the great inland rivers, the Mississippi and its tributaries, deep into the American interior, a journey of over 3,000 miles by water, where a few hundred would have sufficed by land. Only for the final stretch from the river to Fermilab did the ring travel by road, on a specially built truck, creeping along closed highways at night, so slowly that people came out to watch it pass. The move became a small public spectacle, the great white circle rolling through the dark drew crowds along the roadside, and the laboratory shared its progress as the ring inched toward its new home. For a piece of physics apparatus, it was an unusually visible thing, a 15-meter ring of magnet gliding across the country on rivers and roads. Throughout the whole journey, sensors watched for any dangerous flex, and the ring arrived intact, having bent within its narrow tolerance the entire way. There is something fitting in the image. The muon itself is a traveller that survives a journey it should not, born high in the atmosphere and reaching the ground only because relativity stretches its life. Now the instrument built to study it made its own improbable journey, the whole distance around the eastern half of a continent, to survive intact and take up its work again. The particle and the ring were both, in their way, things that made it farther than they had any right to. At Fermilab, the ring was lowered into a new hall and reconnected, and the years of rebuilding began. The magnet was the same, but almost everything around it would be improved. A more intense muon beam to deliver far more particles, better detectors to catch the decay positrons, a field mapped and shimmed to even greater uniformity than at Brookhaven. The goal was to shrink the experimental uncertainty by about a factor of 4, sharp enough to say with real confidence whether the muon gap was real. Rebuilding an experiment of this delicacy is not a matter of plugging the ring back in. It took years of patient work to bring the machine to the precision the physics demanded, and that work is a story of its own. The magnet arrived at Fermilab in 2013, but the experiment, now called E989, did not begin taking physics data until 2017. Those intervening years went into rebuilding everything around the ring to a standard beyond what Brookhaven had reached. The single most demanding task was the same one that had consumed the earlier teams, only harder. The magnetic field had to be made uniform to an extraordinary degree, all the way round the 15-metre loop. Recall why this matters so much. The wiggle in the decay positrons gives the difference between how fast the spin precesses and how fast the muon circles, and that difference depends on the muon's anomaly and on the strength of the magnetic field. Any lump or dip in the field, any place where the magnet was slightly stronger or weaker, would shift the precession and fake a false anomaly. To measure the overflow passed to the precision Fermilab wanted, the field had to be known everywhere along the muon's path to better than 1 part in a million. That is a uniformity almost beyond intuition, a field even to within a millionth of itself around a circle 15 metres across. Achieving it is the craft called shimming. The team placed thin pieces of metal, small iron shims, at hundreds of points around the ring, nudging the field up here and down there, measuring, adjusting and measuring again. They mapped the field with probes carried around the ring on a trolley, building a detailed portrait of every small variation, then shimmed to flatten it. Over many months, the field grew smoother and smoother until it was several times more uniform than Brookhaven had managed. Only then could the muons be trusted to reveal the anomaly rather than the imperfections of the magnet. The beam was rebuilt as well. Fermilab's accelerator complex could deliver far more muons than Brookhaven, and the muons could be prepared more cleanly, arriving at the magic momentum in tighter bunches with fewer stray particles to muddy the measurement. New detectors lined the inside of the ring, faster and more precise, ready to catch the decay positrons and record the wiggle with less noise. Every part of the chain, from the birth of the muons to the counting of the positrons, was sharpened. There was also a discipline the team imposed on itself, one that speaks to how seriously they took the danger of fooling themselves. They analysed the data blind. The number they were after, the anomaly, was hidden from them during the analysis by a secret offset, a deliberate shift known only to a few and locked away. The physicists tuned their methods and checked their work without knowing whether the answer was landing above or below the prediction, so that no unconscious wish could nudge the analysis toward the result they hoped for. Only when everything was finished and frozen would they unlock the offset and see where the muon had actually landed. Blinding is how careful experimenters guard against their own hopes, and on a measurement this consequential, it was essential. The first physics run began in 2017 and gathered data through the following year. That first batch already exceeded Brookhaven's entire dataset, and the team knew that when they finally unblinded, the number would matter enormously. If the Fermilab measurement landed on the old Brookhaven value, the gap with the 2020 prediction would strengthen, and the case for new physics would grow. If it landed on the prediction, the anomaly would begin to dissolve. The world's particle physicists waited for the answer. In the spring of 2021, after years of rebuilding and a careful blind analysis, the Fermilab team gathered to unblind their first result and announce it. What they found would push the muon mystery to its highest pitch. On the 7th of April 2021, the Fermilab team announced the result of their first run. The muon's measured anomaly landed almost exactly on the old Brookhaven value. The two experiments, built decades apart, using the same ring but rebuilt from the beam up, agreed, and together they sat above the standard model prediction from 2020, in the same direction Brookhaven had pointed, only now with two experiments saying it instead of one. When the Fermilab number was combined with Brookhaven's, the gap with the 2020 prediction reached about 4.2 standard deviations. 4.2 sigma. Not yet the 5 sigma traditionally required to claim a discovery, but well past the 3 sigma of the Brookhaven era and close enough to 5 that the room could feel the discovery threshold approaching. Two independent experiments now agreed that the muon was more magnetic than the prediction allowed, and the combined gap had grown to a size that random chance could barely explain. The announcement made headlines around the world. For a field that had waited 2 decades, it was a moment of real excitement, and the language reflected it. Here was the strongest sign yet that the standard model might be incomplete in a way the muon could see, that some undiscovered particle was flickering in the muon's cloud and lifting its magnetism past what the known particles could account for. Physicists spoke, carefully, of possibly standing at the edge of new physics, of a crack in the standard model widening into view. The excitement was earned, but it rested on an assumption, and the more careful voices said so even on the day. The gap was measured against the 2020 prediction, and that prediction's value for hadronic vacuum polarization came from the data-driven road, the one built on electron-positron collision data. The whole 4.2 sigma gap depended on that strong force number being right. If the true value of hadronic vacuum polarization were larger than the data-driven method said, the prediction would rise, and the gap would shrink, and the hint of new physics would fade, no new particle required. And on the very same day as the Fermilab announcement, that caution acquired a face. A calculation had appeared that gave a different, larger value for hadronic vacuum polarization, computed by the other road entirely, and it threatened to explain the gap without any new physics at all, so even in the moment of highest excitement. The muon mystery was already turning into something more tangled than a simple contest between experiment and theory. The measurement was rock solid and getting solider. The question was no longer whether the muon wobbled as measured, it was whether the prediction it was being compared against could be trusted, and that question would come to dominate everything. Before we follow the prediction into its crisis, it is worth pausing on what everyone was hoping for. When physicists said the muon might reveal a hidden force, they had specific ideas in mind, real candidate particles, and forces that a 4 sigma gap might be pointing toward. The dream was not vague. It had names. Because if the muon's anomaly really did sit above the standard model, the excess had to come from something flickering in its cloud, something not on our current list. And theorists had spent decades drawing up lists of what that something might be, each candidate a different vision of what lies beyond the physics we know. To understand what was at stake in the muon's wobble, we should look at the hidden forces it might have been announcing. When physicists said the muon might be revealing a hidden force, they were not speaking loosely. A gap between the measured anomaly and the standard model prediction would mean some particle outside our current list was flickering in the muon's cloud, adding its small contribution to the magnetism. And theorists had a whole catalogue of candidates, each a different guess about what lies beyond the known physics. The muon's wobble was a doorway, and many different rooms lay on the other side. The most celebrated candidate was supersymmetry. Supersymmetry is a proposed deep pattern in nature that would pair every known particle with a heavier partner, a mirror family of undiscovered particles. It was, for decades, the leading hope for physics beyond the standard model, favoured because it could tidy up several theoretical puzzles at once. If supersymmetric partners existed at the right masses, they would flicker in the muon's cloud and lift its anomaly by roughly the amount the gap seemed to show. For years, the muon anomaly was one of supersymmetry's best pieces of circumstantial support. A muon sitting above the prediction was exactly what many supersymmetric models predicted. Other candidates were lighter and stranger. One idea was a new force carrier sometimes called a dark photon, a cousin of the ordinary photon that would connect our world faintly to the dark matter that outweighs visible matter across the cosmos. A dark photon flickering in the muon's cloud could nudge the anomaly. Another idea was a new heavy particle called a Z prime, a heavier sibling of the known Z particle, the carrier of a new force acting on muons. Still another was the leptquark, a hypothetical particle that would let leptons like the muon and quarks talk to each other directly, something the standard model forbids. Each of these would leave its fingerprint in the muon's magnetism, and each corresponded to a different unknown corner of nature. What united all these candidates was the muon's special sensitivity, the mass advantage we met earlier. Because a heavy new particle's effect on the anomaly grows with the square of the lepton's mass, the muon could feel these hypothetical newcomers where the electron could not. A hidden force too feeble to disturb the electron's magnetism in any measurable way might announce itself clearly in the muons. So the muon was not just any probe. It was, for many of these theories, the single most promising place their new particles might first show themselves. The anomaly was the best experimental hint that any of these ideas had. This is why the 4.2 sigma gap generated such excitement. It was not merely an odd number, it was a possible message from one of these hidden rooms, and physicists could not yet tell which room, or whether the message was real. A whole community of theorists built models to fit the muon, adjusting the masses and strengths of their proposed particles to match the observed excess. The muon's wobble had become a target that theories of new physics aimed to hit. And this is also why the honesty required by real science matters so much here. A gap that could be a hidden force could also be a mistake in the hardest part of the prediction, the strong force piece. The two possibilities produce the same number. The dream of supersymmetry, of dark photons and new forces, hung on whether hadronic vacuum polarization had been calculated correctly. If that one stubborn number was larger than the data-driven road said, the gap would close, and every one of these beautiful candidate particles would lose its best evidence at a stroke. That is precisely the reckoning that arrived. On the same day as the triumphant Fermilab announcement, a rival calculation of hadronic vacuum polarization appeared, computed by the other road, and it pointed toward closing the gap. The hidden force had a competitor, and the competitor was not a new particle. It was a supercomputer simulation of the strong force. The rival calculation came from a group known by the initials of the three cities where its members worked: Budapest, Marseille, and Wuppertal, together called the BMW collaboration. In the same season as the 2021 Fermilab announcement, they published a lattice quantum chromodynamics calculation of hadronic vacuum polarization, computed from first principles on supercomputers, with a precision high enough for the first time to challenge the data-driven road head-on. And their answer was different. The BMW value for hadronic vacuum polarization came out larger than the data-driven value that the 2020 prediction had used. A larger strong force piece means a larger total prediction for the muon's anomaly. And a larger prediction sits higher, closer to the measured value. When physicists worked through what the BMW number implied, the gap between prediction and measurement shrank dramatically, from around 4 sigma down toward 1.5 sigma, small enough that it might be nothing at all. The lattice calculation, in other words, suggested there was no muon anomaly. The measurement and the standard model might agree after all, once the strong force piece was computed this new way. This landed the field in a genuinely strange position. Now there were 2 theoretical predictions for the muon's anomaly, from 2 independent and respected methods, and they did not agree with each other. The data-driven road, built on decades of collision data, gave a lower value that left a large gap and hinted at new physics. The lattice road, built on first principles supercomputer simulation, gave a higher value that largely closed the gap. Both roads were the work of careful physicists. Both had defensible uncertainties, and they pointed to different conclusions about whether the muon was revealing anything new. The muon mystery had transformed. It was no longer a clean contest between a measurement and a prediction, the kind of story where you sharpen both sides until one gives way. It had become a contest between 2 predictions, a disagreement inside theory itself, over the value of one stubborn strong force number. The experiment was doing its job beautifully, delivering an ever more precise measurement. But the measurement could not be interpreted until the theorists sorted out which road to their number was correct, and the roads disagreed. This was not a comfortable place to be, but it was, in its way, a healthy one. Science works by exactly this kind of cross-check, independent methods testing whether they agree. When they do agree, confidence soars. When they disagree, it means someone has made an error, or underestimated an uncertainty, or overlooked something, and the disagreement itself becomes a clue pointing at where the truth is hiding. The lattice and data-driven roads disagreeing was uncomfortable, but it was also information. It said that one of the 2 methods had a problem, and finding that problem would teach the field something real about the strong force, whether or not any new particle was involved. The natural next question was which road to trust, and physicists did not want to simply pick a side. They wanted a way to test the 2 methods against each other, to find the specific place where they parted company and see if new data could break the tie. And a tiebreaker did arrive from an experiment in Russia measuring the very collision data the data-driven road depended on. But instead of settling matters, it deepened the confusion, because it suggested the collision data itself might have been off all along. The tiebreaker came from an experiment in Novosibirsk, in Russia, called CMD3. Its job was to measure exactly the kind of collision data the data-driven road relied on, the rate at which electrons and positrons annihilate into hadrons, and in particular into a pair of pions, which is the single most important channel feeding the hadronic vacuum polarization number. If anyone could check the data-driven road at its foundation, it was an experiment measuring that foundation directly. In early 2023, CMD3 reported its result, and it did not match the earlier measurements. The CMD3 value for that pion production rate came out higher than the values from earlier experiments, including well-regarded measurements from experiments called Babar-Clos and Clos. A higher production rate translates into a larger hadronic vacuum polarization, which translates into a higher prediction for the muon's anomaly. In other words, the CMD3 data pushed the data-driven road upward toward the lattice value, toward closing the gap. If CMD3 was right, then the older collision data had been low, the 2020 prediction had been too small, and the muon anomaly might never have existed. But this did not resolve the mystery so much as move it. Now the collision data itself was in conflict. The newer CMD3 measurement disagreed with the older Babar and Clos measurements of the same physical process, and the disagreement was significant. The data-driven road, which had been the gold standard for decades precisely because it rested on real measurements, now rested on measurements that fought among themselves. You could no longer speak of a single data-driven value because the data no longer agreed on what that value should be. So the field faced a tangle with three strands. There was the lattice road, giving a higher value that closed the gap. There was the older collision data, giving a lower value that opened the gap. And there was the newer collision data from CMD3, giving a higher value that agreed with the lattice and disagreed with the older data. The one clean picture of a solid prediction sitting below a solid measurement had dissolved into a knot of methods and datasets that did not line up. Faced with this, the honest thing was to admit that nobody yet knew the true value of hadronic vacuum polarization well enough to say whether the muon anomaly was real. The measurement was superb. The prediction was in turmoil. And the turmoil was concentrated entirely in that one strong force piece, exactly the piece that had troubled the field since the CERN experiments half a century earlier. The muon had done its part. It had wobbled, and its wobble had been measured with growing precision. What it meant depended on resolving a strong force calculation that the world's theorists could not yet agree on. There was, in all this, a lesson that many discussions of the muon skip. The exciting story of a measurement pointing at new physics had quietly become a less glamorous but deeper story about how hard it is to calculate the strong force, and about the discipline of not claiming a discovery when the prediction you are comparing against is itself unsettled. The muon anomaly was becoming a case study in scientific patience, in refusing to declare victory while a crucial number remained in doubt. Through all of this theoretical upheaval, the experiment kept running and kept improving. The Fermilab team had far more data to analyse, and in the summer of 2023 they were ready to report again, with the measurements sharper than ever. While the theorists wrestled with the strong force piece, the Fermilab experiment kept doing what it did best, gathering muons and sharpening the measurement. In August of 2023, the team reported the result of their second and third runs, combining much more data than the first announcement had used. The new measurement was more than twice as precise as the 2021 result, and it landed right where the earlier measurements had, in full agreement with them. This mattered in a specific way. Each time the measurement was repeated with more data and better understanding, there was a chance it would drift, that the earlier value had been a fluctuation or a subtle error that more data would expose. It did not drift. The muon's measured anomaly held steady across Brookhaven, across Fermilab's first run, and now across its second and third runs, the value barely moving while the uncertainty around it shrank. The experimental side of the story was becoming rock solid. Whatever the muon's true anomaly was, the experiments were converging on it with growing confidence, and they all agreed. The improvement came from the patient work of understanding the machine ever better, The team had learned to control the small effects that could bias the measurement, the subtle motions of the muon beam within the ring, the tiny drifts in the magnetic field over time, the details of how the decay positrons were counted. Each source of uncertainty was studied and reduced. The blind analysis discipline continued, the answer hidden until the work was frozen, and when they unblinded the second and third runs, the number sat squarely on the established value, with the error bars pulled tighter around it. By this point, the shape of the whole situation was clear, and it was worth stating plainly. The experimental measurement of the muon's anomaly was becoming one of the most precisely known quantities in all of physics, and it was stable and trusted. The theoretical prediction, by contrast, was in flux, split between the data-driven and lattice roads. With the collision data underneath the data-driven road now in conflict with itself. The bottleneck in the muon mystery had shifted entirely to the theory side. The experimenters were, in a sense, waiting for the theorist to catch up, to settle on a single trustworthy value for the strong force piece, so that the beautiful measurement could finally be interpreted. There was a quiet irony in this. For most of the story, the measurement had been the hard part, the thing that took a 15-meter magnet, a cross-country voyage, and years of shimming to achieve. The prediction had seemed the more solid partner, the theoretical rock against which the measurement was compared. Now the roles had reversed. The measurement was the rock, and the prediction was the thing that trembled. This is not a failure of physics. It is what genuine frontier science looks like, where the last stubborn piece of a hard problem resists long after everything around it has been nailed down. The Fermilab team still had more data to analyse, the later runs that would push the precision further still. And the international theory community, gathered under the Muon G-2 theory initiative, was working toward a new consensus prediction that would try to reckon honestly with the lattice results and the conflicting collision data. Both efforts were heading toward a conclusion that would arrive, for both sides, in 2025. The experiment would give its final, most precise word, and the theorists would issue a new prediction that looked very different from the one that had launched the excitement 4 years earlier. The final measurement came first, in June, and it was the sharpest look at the muon's magnetism that anyone had ever achieved. On the 3rd of June, 2025, the Fermilab team announced their final result, the culmination of 6 years of data taking across all their runs. It was the most precise measurement of the muon's anomaly ever made, reaching a precision of about 127 parts per billion. To feel that number, imagine measuring something and being confident of the answer to within roughly 1 part in 8 million. That is the sharpness the experiment reached on the muon's magnetism, surpassing even the design goal the team had originally set for themselves. The final value drew on more than 20 times the amount of data that Brookhaven had collected. It combined all 6 runs of the Fermilab experiment, each adding its share of muons, each analysed with the same blind discipline and the same relentless control of the machine. And like every measurement before it, the final value agreed with the earlier ones. The muon's anomaly had not budged across a quarter-century of measurement. It had only been pinned down more and more tightly, the error bars closing around a value that Brookhaven, Fermilab's first run, its middle runs, and now its final analysis all shared. This is worth sitting with, because it represents a triumph independent of any question about hidden forces. The experimental measurement of the muon's magnetic anomaly is now among the most precisely known numbers in physics, secured by a chain of reasoning and craft that runs from the polarized birth of the muons through their relativistically stretched circling lives to the wiggle in their decay positrons, all controlled to a few parts in a billion. Whatever the muon turns out to mean, the measurement itself is a masterpiece of experimental physics, and it will stand as the definitive value for many years. No experiment on the horizon will measure the muon's anomaly more precisely soon. The Fermilab collaboration that achieved this was large. Nearly 176 scientists from dozens of institutions across several countries, drawn from many different areas of physics. It took that breadth to build and run a machine this delicate, and to guard the measurement against every subtle way it might have gone wrong. The final result was, in the fullest sense, a collective achievement, the end of a road that the earlier CERN and Brookhaven experiments had begun decades before. With the measurement finished and rock solid, the entire weight of the muon mystery now rested on the prediction. The experiment had said its final word. The question of whether the muon revealed a hidden force came down, completely, to the value of the strong force piece, to whether the data-driven road or the lattice road held the truth, and to whether the international theory community could forge those conflicting inputs into a single trustworthy prediction to compare against this beautiful measurement. That prediction was, in fact, already taking shape. Just days before the final measurement, in late May of 2025, the Muon G-2 Theory Initiative had released a new consensus prediction, an update to the 2020 white paper that had launched the excitement. This new prediction reckoned with everything that had happened since, the lattice calculations, the conflicting collision data, all of it. And it looked very different from its predecessor. The gap that had thrilled the world in 2021 was about to change shape entirely. The new prediction had shifted upward, toward the measurement. To understand why and what it means for the dream of a hidden force, we need to see how the theory community finally chose between its two roads. In late May of 2025, the international theory community released a new consensus prediction for the muon's anomaly, an updated white paper that replaced the one from 2020. The central change was a decision about the strong force piece. After years of the lattice road and the data-driven road disagreeing, and after the collision data underneath the data-driven road had fallen into conflict with itself, the new white paper leaned on the lattice quantum chromodynamics calculations for the hadronic vacuum polarization. And that choice shifted the whole prediction upward. The reasoning was not arbitrary. By 2025, the lattice calculations had matured and multiplied. The BMW result was no longer alone. Other groups, using independent lattice techniques, had computed hadronic vacuum polarization and increasingly agreed with each other, converging on a higher value. Meanwhile, the data-driven road had been thrown into doubt by the conflict between the newer CMD3 collision data and the older measurements. When one of your two roads has grown into a chorus of agreeing calculations, and the other has splintered into datasets that fight among themselves, the balance of evidence tips. The theory community judged that the lattice road was now the more trustworthy guide to the strong force piece. With a lattice value adopted, the new prediction rose to meet the measurement. In the words of the theory community, adopting the lattice calculations produced a major upward shift in the predicted anomaly, one that implied there was no tension between the standard model and experiment at the current level of precision. The gap that had reached 4.2 sigma in 2021, the gap that had launched headlines and revived hopes for supersymmetry and dark photons, had largely closed. Measured against the 2025 prediction, the muon's anomaly sat right about where the standard model said it should. This was, for the dream of a hidden force, a deflation. The tantalizing excess that had seemed like a window onto new physics now looked, most likely, like the consequence of comparing a superb measurement against a strong force calculation that had been slightly too low. The muon was not, after all, obviously pointing at supersymmetric partners or dark photons or new forces. It was, as far as anyone could now tell, behaving exactly as the known particles in its cloud required. And a further calculation, published in early 2026, brought theory and experiment into agreement to a remarkable degree, tightening the case that the anomaly had been a theory problem all along. It is important to say this plainly, because the honest ending is not the exciting one, and honesty is the point. The most likely reading of the evidence as things stand is that there is no muon anomaly, that the hidden force the title asks about has not revealed itself in this measurement. The strong force piece, once computed with the more trustworthy method, accounts for the muon's wobble without any new physics. But there is a caution to hold on to, and the theory community holds it. The lattice and data-driven roads still do not fully agree at the finest level of precision, and the conflict in the collision data is not fully understood. The theorists are still working to reconcile the two methods and to explain why the older collision data came out low. Until that is settled, the door is not slammed shut, only mostly closed. A summary from within the field put it well, that one of the most intriguing anomalies in particle physics is severely undermined, but not yet definitively resolved. The wonder has to stay honest, and honesty here means holding both the deflation and the small remaining doubt at once. So the direct question of the title has an answer, and we should give it plainly before widening out to what the whole long effort was really for. So was there a hidden force? The honest answer as things stand is that there does not appear to be, at least not one the muon's magnetism has revealed. The excess that thrilled physics in 2021 has largely dissolved, not because the measurement failed, but because the prediction it was compared against was refined. Once the strong force piece was computed with the more trustworthy lattice method, the muon's wobble turned out to match the standard model. The tantalizing gap was most likely a gap in a calculation rather than a crack in nature. For anyone who had hoped the muon was announcing supersymmetry, or a dark photon, or some new force acting from the shadows, this is a disappointment, and it would be dishonest to dress it up as anything else. The muon was the best experimental hint many of those theories had. When the gap closed, that hint faded, and the beautiful candidate particles lost their most concrete piece of support. Nature, as far as this measurement can tell, kept her hidden forces hidden. But it would be a mistake to call the whole effort a letdown, and here is where the honest story becomes, in its own way, a triumph. Consider what was actually accomplished. Physicists measured a property of a fleeting particle to a precision of about 1 part in 8 million, a number secured by a 15-meter magnet floated across a continent, by relativity stretching the muon's life 30-fold, by the lopsided decay that lets an invisible spin be read from a spray of positrons. That measurement is now among the most precise in all of science, and it will stand for years. The experiment did not fail. It succeeded completely. It told us, with extraordinary confidence, exactly how magnetic the muon is, and the effort forced something else, something that would never have happened otherwise. It drove the calculation of the strong force to a new level. For decades, the hadronic vacuum polarization was the weakest link in the prediction, the one stubborn piece nobody could pin down. The pressure of the muon anomaly pushed the lattice method to mature, pushed the collision experiments to remeasure, and in doing so exposed a real disagreement between methods that is teaching physicists about the strong force itself. Had the experiment never been done, the field would have been left with two theoretical camps quietly disagreeing and no way to know which was closer to the truth. The muon measurement is what revealed where the difficulty actually lay. It turned a hidden weakness in the calculation into a visible problem that can be worked on. There is a lesson here about how science actually proceeds, and it is worth carrying away. The dramatic outcome, a new particle, a hidden force, did not arrive. What arrived instead was a hard-won piece of understanding that the muon's magnetism is exactly what the known particles predict, and that the strong force is even harder to calculate than anyone had fully appreciated. That is a real result. Ruling out an anomaly is not the same as learning nothing. It narrows the map. It tells the theorists chasing new physics that this particular door is most likely closed, so they should look elsewhere through other doors that remain open. And many doors do remain open. The muon has not finished being useful just because this one anomaly faded. It remains the heaviest lepton we can catch and hold, still the keen microphone tuned to frequencies the electron cannot hear. There are other muon puzzles, other experiments, and a new measurement of this very anomaly being planned with a completely different technique. The muon story is not over. It is entering its next chapter. The muon anomaly may have faded, but the muon itself remains one of physics' most valued tools, and several efforts will keep it at the centre of the search for new physics. The first is a plan to measure the very same anomaly again in an entirely different way, at a laboratory in Japan. At the Japan Proton Accelerator Research Complex, known as JPARC, physicists are preparing an experiment that will measure the muon's anomaly using a method quite unlike the Fermilab approach. Rather than sending muons around a large ring at the magic momentum, the JPARC experiment will cool muons down to very low energies and then accelerate them in a much smaller, more compact setup, without relying on the magic momentum trick at all. Because the method is so different, it will have entirely different sources of error. That is exactly what makes it valuable. If a very different experiment, with different ways of going wrong, measures the same anomaly and gets the same number, confidence in the measurement grows enormously. The JPARC measurement is expected in the early 2030s, and though it will not immediately match Fermilab's precision, its independence is its strength. A measurement confirmed by two unrelated methods is far harder to doubt than one. Beyond this specific measurement, the muon figures in bolder plans for the future of particle physics. One of the most ambitious is the idea of a muon collider, a machine that would smash muons together at very high energies instead of the protons or electrons used today. Muons offer a tempting combination. They are heavy enough to be accelerated to high energy without losing as much energy to radiation as light electrons do. Yet they are simple, point-like particles, unlike the messy composite protons. A muon collider could, in principle, reach energies and cleanliness that other machines cannot, opening a new window on whatever heavy particles might lie beyond current reach. The great obstacle is the muon's short life. Building a collider from particles that decay in microseconds is a formidable engineering challenge, and it remains a hope rather than a plan, but it is a hope that keeps the muon at the frontier. The muon has also been at the heart of other puzzles beyond its magnetism, reminders that this particle keeps raising questions. There was a puzzle about the size of the proton, measured using muons orbiting in place of electrons, which for years gave a proton radius that disagreed with other methods before being largely resolved. There have been questions about whether the muon and the electron truly behave identically in certain decays. Tests of a principle called lepton universality, which have seen their own dramas of apparent anomalies rising and then fading under scrutiny. The muon has a habit of sitting at the edge of the known, generating hints that force physicists to measure and calculate more carefully, whether or not those hints survive. This pattern is itself worth appreciating. The muon, the particle nobody ordered, has spent its scientific life as a provocateur. It arrived without a purpose, was mistaken for something it was not, and then, precisely because of its inconvenient heaviness and its fleeting life, became a uniquely sensitive probe of nature's deepest structure. Again and again it has produced anomalies that drove physics to sharpen its tools. Some of those anomalies dissolved, like the magnetic one appears to be dissolving now. But each one left the field more precise, more careful, and better equipped than before. So the muon's next chapter is not a search for a lost anomaly, but a continuation of its long role as a testing ground. New measurements, new techniques, and perhaps one day new machines will keep asking the muon what it knows. And that brings us back, at the end, to the oldest question anyone asked about it. The question that has quietly organised this whole story from the beginning. Who ordered that? When Isidor Isaac Rabi asked his four-word question, he meant it as a wry complaint about a particle nobody had asked for, a heavier electron that seemed to serve no purpose in the tidy world of atoms. We can now answer him, and the answer is richer than the question expected. Nobody ordered the muon. It is simply there, the middle child of three lepton families whose very existence physics still cannot fully explain, and that unexplained, unordered particle turned out to be one of the finest instruments nature ever handed us. Return to your hand, and the muons passing through it right now, borne miles overhead in the cosmic rain, reaching you only because relativity stretches their brief lives. Each one is a tiny magnet, spinning in the quantum sense, dressed in a shimmering cloud of virtual particles that flicker in and out of the emptiness around it. And the exact strength of that little magnet, the overflow past Dirac's perfect 2, is a census of everything that cloud contains, seen and unseen. That is what made the muon worth chasing across a century, across an ocean of rivers, across a quarter century of ever finer measurement. Its magnetism is a way of asking the universe what it is made of. The title asked whether the muon mystery may reveal a hidden force, and we have followed that question honestly to its present answer. As things stand, it appears not. The tantalizing gap that once seemed like a window onto new physics has largely closed, explained not by a new particle, but by a better calculation of the strong force. The most likely truth is that the muon is behaving exactly as the known particles require, and the hidden force, if there is one, is not the one this measurement seemed to show. Wonder, kept honest, sometimes leads to a quiet answer rather than a loud one. But look at what the asking accomplished. To settle whether the muon revealed a hidden force, physicists measured a fleeting particle's magnetism to about 1 part in 8 million, built and moved a magnet the size of a house, leaned on relativity as a working tool, and pushed the calculation of the strong force to a precision it had never reached. They found no new force, and in finding none they mapped the boundary of the known more sharply than ever, and they exposed exactly where our grip on the strong force is weakest, which is where the next understanding will come from. A closed door, clearly seen, is worth more than an open one imagined. And the muon is not finished. A new experiment in Japan will ask the same question a different way. Bolder machines may one day accelerate muons to energies we cannot yet reach. The particle nobody ordered will go on doing what it has always done, sitting at the edge of what we know and quietly insisting that we look closer. There is something to carry away from all of this, something larger than one particle's magnetism. The universe you belong to is not fully mapped. Its deepest rules are known well enough to predict a muon's wobble to 8 digits, and not so well that we can be sure nothing hides beyond them. We live inside that gap between what is measured and what is understood, and the whole enterprise of physics is the patient work of narrowing it, one stubborn number at a time. The muon, streaming silently through your hand as you sit here, is one of the ways the universe lets itself be questioned. And we are, remarkably, the kind of matter that has learnt to ask.